Okay, so I've got my solenoid connected to my power supply, and we've looked at the fact that anytime you've got electricity or moving charges, those moving charges create a magnetic field. And if I've got a coil of wire, that magnetic field is pointing in a particular direction inside the coil of wire. And if I have lots of coils of wire, I've got a pretty strong magnetic field inside. So what's going to happen is when I turn this thing on, like so, I've got a huge magnetic field in there. But the problem is our eyes can't see magnetic fields. So how do I know that? So a couple things. We can see the effects of a magnetic field. We can see how a magnetic field might affect a compass. So here's my compass. And if I turn this on, we see that it actually moves. Okay, so there's got to be some kind of magnetic field in order for this to move. I've got paper clips, and paper clips are definitely affected by magnetic fields. So if I have my paper clips here, let's see. Oh, hey, get those out. Wait, gotta get those out. Where'd they go? Okay, so you can see that they're definitely like attracted to this, and I'll show another viewpoint of this as well. And you think, no, that's not a very strong magnetic field. I can actually take a magnet and have it be attracted to that as well. So same thing, I can bring my magnet in and it's attracted as well. I'm going to show you another viewpoint of this so that you really believe me on the magnetic field. Okay guys, so same setup, just different orientation. I still have my power supply, I still have my solenoid right here. I'm just going to run the electricity, turn the electricity on. There's a magnetic field being created because there's a bunch of electricity going through these coils, creating a pretty strong magnetic field in the center. And here are my paper clips again. They're just getting like sucked up, and if I turn the power supply off, they just fall out. Okay, so there's no attraction. And it's a pretty strong magnetic field, like it's enough to even pull up this bar magnet. If I and then again, if I turn off the power supply, there's no magnetic field. It's not attracted. Sorry if that was loud. Induction. So this is actually my old doorbell. So I took it off the wall, and I'm going to open it up, and when I take off the casing, I see that there is where I have my input and my output. So this is like where my electricity goes in, and inside that is actually a solenoid. So what happens is when I put electricity into these two terminals, a current goes through that solenoid, and a magnetic field is generated in that little solenoid. And so if I've got a magnetic field, I can attract or repel something magnetic. Well, this little shaft here, this part is magnetic. So this will either get attracted, well, actually it gets attracted in to the solenoid. But there's this little spring that says, hey, if I'm not attracted, I'm going to bounce back out. So an external mechanism can make it go in, but if that external force is not there, it'll just bounce back out. Okay, so if I just connect this by itself, you can see that mechanism happen. Or if I turn my power supply on, oh, I disengaged too far. Okay, so we see that attraction. When the current is running through, I create a magnetic field, I attract this. Now how this works in the overall system, and I have to disengage this to be able to connect this properly, is that this guy is housed right here inside. So if I connect it again, here we can see, I'm going to turn it on. So when it's engaged, it hits this piece of metal here, and when it's disengaged, it hits this piece of metal. So I get my doorbell. Okay, and so here we get the ding, dong. Look at these two pieces of metal. They are totally different sizes, and we know that if you hit something, you strike something, it'll always vibrate at its natural frequency. And natural frequency is determined by the size or the material of the object. So this is going to be shorter. So because this is shorter, it's going to have a higher natural frequency, and this is longer, so it's going to have a lower natural frequency. So that's why we get the high-pitched ding and the low-pitched dong, dong. And then if you put the housing on, the housing is just there to say, hey, sound waves. Oops, I disconnected. Hey, sound waves, we're not going to let you travel outside of this. You have to just continually vibrate and interfere inside this mechanism. Oh, I think I just disconnected. This is tricky. Okay. So this just forces those sound waves to interfere and add up constructively within this box, and so it gets louder. So, an application of electromagnetic